Instantaneous acceleration. Instantaneous acceleration is your acceleration at a moment in time. We have a curve along this velocity time graph, and we're going to pick a point along that curve, and if we found the slope at that position, it would be your instantaneous acceleration, because it's your change in velocity over your change in time. Now, acceleration is the first derivative of your velocity with respect to time. It is also the second derivative of your position with respect to time. If we look at an example equation, x equals at squared plus b, take the first derivative and you have 2at. Take the first derivative of your velocity and you have acceleration is equal to 2a. A is just some constant that would be given to you. So an example, a particle's position is given by this position equation. X equals 2.1 meters per second squared times t squared plus 2.8 meters. Calculate the instantaneous velocity as a function of time. They're only asking for the equation for the instantaneous velocity. So if we take the first derivative, we have 4.2 meters per second squared times t. Part B asks us to calculate the average acceleration from 3 to 5 seconds. So average acceleration is your change in velocity over your change in time. So we need to find the velocity at 3 seconds and 5 seconds, and then find their difference. We use our first derivative of the position equation, 4.2 meters per second squared times t. We're going to plug in 3 first to find the first velocity, and we get 12.6 meters per second. Notice my seconds do square. The units can be canceled. Our second velocity is at 5 seconds, so 4.2 meters per second squared times 5 seconds gives you 21 meters per second. Our time difference is 2 seconds. To find the average acceleration, subtract your v1 from v2 and divide by the time difference, and we have acceleration is equal to 4.2 meters per second squared. Part C asks us to find the instantaneous acceleration. So if we take the first derivative of the velocity, we have a equals 4.2 meters per second squared. Notice that's a constant. It's not changing. There's no time variable. So we have the straight line for a versus t graph. It is unchanging. Let's look at another example. This time, we have a position of a particle given by this position equation. We have 2 meters per second cubed times t cubed plus 2.5 meters per second times t. What is the acceleration at t equals 2 seconds? So I want acceleration at a particular time. So I want the instantaneous acceleration. Take your first derivative, which is v equals 6 meters per second cubed times t squared. All right, so it's 3 times 2 to give me the 6, 3 minus 1 to give me the t squared. On this section, t has an exponent of 1. 1 times 2.5 gives me 2.5. The t drops out because now its exponent is 0. Now we take the derivative of the velocity. So t squared be 12 meters per second cubed times t, and this time the 2.5 drops out. To find the acceleration at 2 seconds, plug in your 2 seconds, multiply by 12, and we have 24 meters per second squared.